Okay, so I saw some family also came in into. So yeah, my talk is going to be Richardson-Gaudin integrability in quantum many body systems, and I kept quantum many body systems, not so much nuclear, but actually this time it will boil down to that. So I'm in the Department of Chemistry. It speaks for David's accomplishments that of what we did scientifically. So it speaks also for David. I think that is also one of his achievements, his wide, large spectrum and interests sort of was given down to us. Yeah, so here's an outline of people's, but nevertheless, I'm going to. So first, a little bit talk about David, and then how I got to Toronto, and how I moved away from Toronto in the end and ended up in quantum. So here it is. Probably these two people up here, permanent in my education as being a. Here's my PhD super. I did my PhD in nuclear structure physics at university, and this one, this. Now I did my the nuclear physics community. Kelly, who used to be, I think, Mark stock advisor, had just solved a potential which sort of was like the phase transition between two types of collective motion, like look like so they can rotate. Physicists are very interested when stuff changes. So Franco had solved that, and there was a big push then to communicate new, etc. So Chris, when I and this looks like an. So you go and try to investigate that phase transition a little bit more from vibrational to rotation. But in order to do that, you have to learn. Okay, so I started embarking into that, and Chris was chair of the department. I was trying to fiddle really fun solution, whatever. And then John Wood came. He said, "Oh, you should talk to," because he figured it out, right? And he figured it out. These and blah blah blah, and I didn't really like that because I've written or developed way and have a numerical thing. So I started looking further and further and further into it, and got some collective model. In Athens, group structure, and we got well, we understood. We had a language, a common language to each other. So when then the created, and I wanted to David, I had my own money, and he said, "Yeah, sure, come over, right? We can talk about a lot of stuff." So this basically brings me to one of the things that characterizes David's quote from him. He said, I talked later to him, he said, first you try to solve the problem, and then when you're stuck, you look into the literature, but not too much, right? Because there's always this tendency trying to understand everything as much as possible from his own. Now, this is not the only thing that I learned from David. There's other things. So the stuff that I learned from David was, first of all, whatever you do, try to get the physics, okay? This puts him a little bit aside from is that he wasn't only interested in the mathematical stuff, and it always had to, right? It always had to or the problem that you were interested in. And the second thing is, it has to have some mathematical. The right one, okay. Whoops. Oh, I think this is, I put the picture here. This was at a workshop at INT in Seattle. Here's David explaining something to my, how would I say, postdoctoral mentor, Lorenzo. Look careful. This is me here trying to catch up with both. It's actually a nice, well, fun story. So this was at Seattle. We were supposed to fly back to Toronto at the end. I'll set up here my, and so we started chatting about this. Oh, you could do this. Oh, we can look into this and blah, blah, blah. And then suddenly saw our flight taxiing away before us. And like, oh my God, we missed our flight. So we went to the desk, and then like, oh, nobody called us, right? And then the person said, oh, that's not true, because I personally called. Like, and I thought, right? So, oh. So, and she butchered it, right? And I said, oh my God. She said, yeah, that may be true, but that doesn't work for you, Mr. Rowe. So yeah, we got on a flight, and then ever since, like, missing our similar thing. But it was this, let's say, like this charism that particular time. I've never missed a flight until that date. I've never missed it ever. Just so exciting talking. Okay, so now it's time. Yeah.
Sorry, Stijn. Yeah, but yeah. Sorry, I think the audio becomes choppy when you move away from the console.
You want me to be static here? Is that what it is?
No. The Zoom audio becomes very choppy whenever you move away from the console.
Okay, this is against my style of presenting, but I'll do it.
I know. I think you can go like 2 meters away. No, 1 meter away. But beyond that,
I have
we
thing
can't
here
hear
as well.
you. Yeah.
But I'm not sure. I think it's turned on. No. Should I? Is it now better?
Yeah.
Yeah. Okay, I'll just stand here. Okay, so yeah, the quantum antibody problem. So that was the reason why I went to Toronto then afterwards, to just work further on this notoriously difficult problem. So this is the job this is what we try to do. Right? So what do? We first construct the A-body Hamiltonian. Okay, so the energy operator for the system, and then we try to solve the Schrödinger equation, which boils down to be an eigenvalue equation. And now let me use a quote from another famous British physicist, Paul Dirac, who basically already, like, you should realize this is the 20s when Dirac said this. Quantum mechanics was being developed as we speak. Like 2 years before that, he had his famous equation, and then he wrote this in 29. I'm going to read with you. So the fundamental laws necessary for the mathematical treatment of large parts of physics and the whole of chemistry. So this is before high energy physics. The whole of chemistry, so electrons, so this is fully known. And the difficulty lies only, note the only up here, in the fact that application of these laws leads to equations that are too complex to be solved. And as a matter of fact, 90 years later, or almost 100 years later, we're still struggling with that. But what does it mean? What does Dirac mean? Right? Are we too stupid to do that? Do we miss the intellect? No, it's not that. So we do not miss the intellect to solve these things. It's just they're too difficult. And here is the reason why. So one of the things that I call this configuration interaction, this slide, one thing that we take for granted, and actually it's not so much for granted, is that usually the systems that we're working with are bound systems, okay? Which means that we can embed them within a mean field, okay? So here we have, and this is a bit of a schizophrenic talk because I'm going to be using pictures from chemistry and nuclear physics together, but here you can think in terms of like protons and neutrons, and they're attracted to each other. However, what happens is they sort of create this mean field for each other. Okay, so here you have this mean field one body potential, and you subtract that from the two body potential. So what you end up with is a residual interaction. Okay, so you kind of hope that you put much as possible into that one body potential. Think of your 3D harmonic oscillator. We heard about that today, and then everything else should be residual. Now, these residual interactions then are treated in active valence space. Okay, so we created now these orbitals up here. Okay, and now these particles go and live into these orbitals. And now each of the configurations, so each distribution of blue and red particles along these orbitals, okay, is going to give a new configuration, and we call those Slater determinants. Okay. Now, if we were living in a classical world, then our nucleons, would pick out one of those orbitals and be very happy there. Okay, they would just pick up one of those. However, we live in a quantum world. So basically what we have to do is we have to take a linear combination of all those classically allowed configurations. Now, what I've given here, and this is a chemistry plot, but the same applies for nuclear, is everything depends on what this dimension, so the sum runs over I from 1 all the way up to the dimension of the Hilbert space. Now, what is the dimension of the Hilbert space? As long as that is tractable or is small, we should really, the problem is solved. We put a computer and that gives it to us. However, this is where the issue is. This is the issue that Dirac already saw. So here we have typical curves, blue curves, and then labeled by the number of particles. So in this particular case, it would be electrons. So methane, for instance, has 10 electrons. Iron has 26. Caffeine, my favorite molecule, has 102 electrons. And these are, this L is the number of orbitals that you allow them to sit in. Okay. So here is a dimension. So how many terms we need to take into account as a function of the number of orbitals that we have to give them. And eventually we want to give them a lot of orbitals. Okay. And what you see here is that those curves, they just go through the roof immediately, right? So note this is an exponential, logarithmic scale. Immediately, as soon as you open up a little bit of space for them, the space immediately, a couple of orbitals, the space immediately explodes. Now, here for a reference is a red line, which is the number of numbers that you can store into 1 gigabyte RAM. Okay, so that is the working memory of your computer. Okay, so if I want to do anything with that, I hope that I can at least put that in my RAM. So that is that number up here, this red line. So what you can see here is that for almost any system that you think of, like 10, 26, 42, 102, I think that will be cadmium in the nuclear case, it immediately blows up in your face. So that's the problem. Okay, that's the problem that we're facing. Okay, so how do you solve that problem? You solve that problem by being a physicist, trying to extract the essential degrees of freedom that you need. In the same way that David and George realized that you needed the quadrufold degrees of freedom to describe atomic nuclei. Okay, but there are more. Okay, there are more. So one of them is pairing. It's sort of like the orthogonal one with respect to quadruple deformation. Now, if you look at those residual interactions that I talked to you earlier, and you do how would I say, you compute them in a recoupled angular momentum basis. Okay, so JJ is the same orbital, and you couple them to larger J, then you get to typically such a curve in which the J equals 0 component is very strong, and everything else is largely suppressed. Okay, which basically means that you can approximate these residual interactions to just those that have the same angular momentum 0. Okay, have the same couple to angular momentum 0. How can I interpret that? Well, nucleons are strongly attracting each other. Okay, so they would preferably sit together in the same spot, but that's forbidden by the Pauli principle. Okay, so they cannot just like sit on the same spot in space. So what's the next best thing is that they go in an orbital and then they try to get each other, they encounter each other once every half a turn, right? And that is exactly what's happening here, is that the rotation of one nucleon is counteracted by the rotation of the other one. Now, if you do that and you do some mathematics, then what happens is you get to the pairing Hamiltonian. Okay, so here we have a Hamiltonian. This would be my single particle, so the mean field. These would be these residual interactions, and they're limited to pairing. And here I have created, well, I've written down these S operators. those are the creation and the annihilation of a pair. So it's really the interaction between pairs. Now, what is crucial here is, and this is again, if there is also something that Arthur referred to, if there is a nice solution to a problem, it's probably a symmetry. So what you can do is you can rephrase this problem of pairs. It's into SU2 algebra. So it's a quasi-spin that's associated. Okay. So now, coming back to this one, Richardson solutions to the BCS. If we do a further reduction, further simplicity, so in the previous one, I allowed for interactions, pairs, to be dependent between all the different orbitals. Now, if we don't do that, so if we say that everything is orbital independent, then we come up with the famous Bardeen-Cooper-Schrieffer Hamiltonian, which was originally proposed for nuclear physics by the same Rowe and Mottelson that we've already heard about today. So what is Richardson's solution to the BCS Hamiltonian? So the reduced BCS Hamiltonian, given up here, is diagonalized by means of a beta ansatz wave function, which looks something like this. So it is a wave function, it's a product wave function of generalized pairs, S alpha dagger. So this is a generalized pair, which I'm writing as a linear combination, a weighted linear combination of original pair operators. So it's a sum over SI dagger weighted with single particle energies that come from the mean field with some parameter x alpha, which I for now will call the Richardson variables, Richardson parameters. Now, this is only an eigenstate provided that the three Richardson variables x alpha satisfy the so-called Richardson-Gaudin equations, and they are here given at the bottom. Okay. So recap: this is the Hamiltonian. We have a product state as an eigenstate, the beta ansatz eigenstate, provided these parameters x alpha solve this set of equations. Now here is something very interesting happening. Why? Remember that this number of coefficients that I talked to you that was scaling exponentially was going through the roof. Now, what we see here is that the number of free parameters, or the number of free degrees of freedom that I have to characterize the system, does not scale exponentially, but it scales linearly. Okay? So I have with each of pair of particles, I have another parameter. Right? So if I suddenly, for my 102, which would be cadmium or caffeine for chemistry, I do not have to do something like exponent 10 to the power 102 coefficients. No, I have 102 that I can store very easily. Okay, so there's an opportunity there. Okay, so how does that work? So here is for, I think, a model calculation for tin. Yes, tin 120. So this is how it looks like. Okay, so you solve this thing. Okay, so you have your parameters that is given by the mean field. So epsilon I comes from Hartree-Fock. So you have those are real parameters. So you see here I put them on imaginary real plot. And then what would happen is that these x alpha, once you solve them, they organize themselves in this complex plot. Okay, like that. Okay, so we have the wave function. And so as soon as we have those x alphas, we have the wave function. Now, okay, when something should move, when you have a simple solution, then there is some symmetry associated. I already alluded to SU2, but that's not the whole story, because this whole story here is integrability. Turns out that the Richardson Hamiltonian is an integrable system. What does it mean? An integrable system, I'm going to use a very loose definition because I don't think there is a closed definition right now. So a quantum system is integrable when its Hamiltonian supports as many conserved quantities as degrees of freedom in the system. Okay, so dynamical symmetry, that was the word I was looking for, is, for instance, so EtAlors IBM, for instance, is an integrable system. But this one is a little bit more general. Special case, when our Hamiltonian is built from those conserved charges. Right? So let's say we have conserved charges. Okay, so they all commute mutually. So I have L degrees of freedom, let's say L orbitals. Then if my Hamiltonian consists of those that commute mutually, then they also commute with all of those conserved charges. Right? Now, for the reduced BCS Hamiltonian, what do they look like? Well, they look something like this Ri operator. Okay, so we have like the central thing, and then an interaction, which it looks a little bit like a spin-spin interaction between one of the labels and all of the other ones. Now, this conserved charge allows us to make a connection with other domains of physics, because this one looks exactly like a magnetic interaction. So the SU2 quasi-spin allows us to make a connection with spin. And once we have spin, we can also talk about magnetic systems. So this one is actually pretty well known. It's called the central spin, in which the central spin particle is interacting with the bath of all the other ones. And so it's proposed also as a model for quantum computing, but I'm not going to go into that here. Now, here's a little bit of a technical thing. So if you require these to be integrable, then what turns out is that these three parameters, x and z, they have to fulfill this Young-Baxter-Gaudin algebra, which is now perfectly solved and understood. Okay, good. So we have Richardson-Gaudin integrability, and then typical question what I get is like, isn't it WhyBotherson-EtAlors integrability instead of Richardson-Gaudin integrability? Well, and here again comes back to David, right? Because David did not only understand stuff that was mathematically elegant, but he also saw when there's opportunity, right? So just for the sake of it was not typically not something that would trigger his interest. It's typically when there would also be an opportunity. So when I was talking about these things with David, we talked about it, and instead of like embarking on was in the airport, not in the airport, but shortly after, we agreed that I should not so much work on symplectic stuff, although this is also a symplectic model. However, more into what are the challenges and the opportunities for this thing. Okay, challenges and opportunities. So one of the challenges at the time was that these Richardson-Gaudin equations, they're plagued by what we call singularities. Okay. Why singularities? You can sort of see what's happening here. Basically, if you have a little bit of a let's say, electromagnetic look into that, you can really look into these x alphas and these epsilons as charges, okay? And then there is these ones. I would say they're sort of attracted. So the x alphas would be attracted to the epsilons, but they would repel each other, right? So see, there's this plus sign up here, but there's a minus sign up there, right? So there's this competition between the two things, and then you have something here that sort of like skews everything. So you get this dynamics in which charges are attracted to single particles, to single poles, but they don't really like each other. And this is the dynamics that you see here if you try to solve these equations as a function of this as a pairing strength G. And you would have all these points here where, as a quasi point there, where the variables, they would coalesce, the Richardson variables, and these things becomes like adding up and subtracting infinities, right? Again, following David's credo, the person who was very much into this, introduced this to the nuclear physics community, was Jorge Dukalski. So I asked, like, how do you solve them? Well, you basically talk to my postdoc and he will give you code. So then we went back to the first credo of David's. First, you try to solve the problem yourself, then you look into the literature. And I was here in Toronto, so I learned a lot about collective motion together with Shen Yang. I learned a lot about bosonic modes, and I also read the book that Mark brought to the workshop. And one of the solutions, one of the topics that was discussed there extensively was random phase approximations and also Tam-Dankov approximation. And one of the for how would I say, very schematic Hamiltonian, this set of equations on the right-hand side came about. Now, if you look at this one and you look at the previous one, so this Tam-Dankov approximation is actually, it's hidden in here. You see that, right? So it's as if everything is beautifully, there's just like, there's no repulsion between them, right? So if between those variables, so that would be very, if we can map this to the Tam-Dankov circular equation. It's called the Tamdankov circular equation. We would be in business. Okay. So that brings us back. What is a Tamdankov approximation? Well, it basically assumes everything is bosonic. And if stuff is bosonic, then the Hamiltonian, or the wave functions, the eigenfunction of the Hamiltonian, they have this product wave function, which is even worse than product wave function. It's a polynomial. It's bosonic mode to the power of n. Okay. And then if you generalize that boson, you create a generalized boson, then you find all the eigenstates h bar omega by solving this circular equation. So a nice thing of this is you can just plot it. So you plot this function, and then you just look at the roots. So you don't use SymPy. SymPy didn't exist. Okay, so how do you get there? Well, learning more about algebras, learning more about group theory. I also learned about deformed algebras, how Heisenberg-Wiles were embedded within SU2 and all those sort of businesses. And that got me inspired by trying to map an SU2 algebra into a bosonic algebra. And this is the way how you can do it. Okay, so here, this is the algebra for SU2, and so the typical creation annihilation operators as dagger as I, and also the projection as I, and the clue is here. Okay, so the key is here, where the S dagger as I, typically we have psi equals 1, so this constant up here disappears, and we have this operator, and then we have SU2. However, if we now would take psi equals 0, then this term, this operator, would cancel, and we go back to a bosonic algebra. So this psi holds the key to turn a fermionic pair into one boson. Okay? So it gives us the tool to turn Richardson, well, the reduced BCS Hamiltonian, Richardson's Hamiltonian, into a set of TDAs, bosonic. And as lo and behold, if you do the whole theory for Richardson-Gaudin, and you do it with this deformed algebra instead of the normal, the psi just pops up at the most convenient place that you want it to be. Okay, so here in this repulsion. Okay, so what was the significance? Psi equals 1. We obtain the standard equations as before. Psi equals 0. We turn this into a bosonic. So then here is the picture. So this was for 118 tin. First of all, you did the TDA, and from the TDA, by cranking up deformation parameter back to its origin, we were able to, as a matter of fact, solve those rich. So the challenge had been solved at that time. Okay, typically what happens then, you work on a problem for so many years, you hire a very excellent, brilliant student, Peter Kleis, who basically comes about and tells you that what you did was actually great, but you could do it much quicker and much more beautiful. So he worked on the eigenvalue-based method, in which is actually pretty beautiful. If you look back at those central spin Hamiltonians, those conserved charges, there are expressions there that for the square of that of those conserved charges, and then you bring it back, they sort of reduce and map back onto a linear combination of the original ones. So you can turn this problem immediately into a problem on the eigenvalues of the operator, and basically solve it in a much more smooth way, where you don't suffer from all these singularities, where everything lives as smoothly as possible. This is for another model, XXZ, that I'm not going to be talking about. It's for condensed matter physics. Okay, so that was the challenge. The challenge has been solved. Okay, now what's the opportunity? So here is the opportunity. So remember the first slide, we embedded this bunch of fermions into a mean field, okay, and then used the fact that everything was and the hope that these residual interactions were going to be small. Now let's do the same thing. Let's do the same thing. However, not embed them within a mean field, but embed them within an integrable model, right? Which is basically the same idea that you embed the interaction, the nuclear interaction, into a symplectic basis, right? So you try to optimize all of the correlations such that everything else is small, right? And then what one can do is one can use these beta ansatz wave functions as improved basis, not so much the Slater determinants. And then you can do a lot of stuff, right? So you can integration interaction, and basically crank the standard stuff that people are doing. There's function theory, whatever. Okay. However, and this is actually one of the few workshops where I don't have to introduce the word permanent, because somebody else already did it before me. Typically, I have to do it myself. But here it is. So this brings me if you wanna compute those interactions then where you want to work with in this new basis, you also must be able to compute all the matrix elements, right? Now, it was known in the past that if you take a generalized pair, okay, so here it is again. So here's a generalized Richardson state, as to say. So it's a product of generalized pair operators. And then you want to express this in a computer, so you project it on a Slater determinant. What happens is that you end up by computing the permanent of this matrix G. Okay, it's a subset of this G, but you get the idea. Now, the issue is that no matter what you do, well, that's not true, but in the most general case, you end up with a factorial scalar. Okay, so I don't know if you remember what the difference is between a permanent and a determinant. Probably I don't have to talk to you in this community. It's determinant, but without the minus sign, right? It's with the plus signs. Now, there's just a handful of theorems, and it just, yeah, it's a roadblock, right? So you can't do anything. However, in our case, we remember we had these generalized pair operators, product state of generalized pair operators. However, there is a famous, well, not famous, but for me, it's famous by now. There's a Borchardt theorem that reduces the states to a ratio of two determinants, where the star up here is a Hadamard product between two. Yeah, it's where it's like an undergrad's dream come true, where you just take the two elements of and you multiply them elements wise, right? No matrix multiplication. And even better, there's a Slavnov theorem in integrability that tells me if I'm computing Richardson states with respect to another Richardson state because it's slightly different, then it just reduces to determinant. So this means that one can do a variational theory with these integrable models, which is great, and it's exactly what we did. So here what we have, it's a non-integrable pairing model. So here is this the dependent, more realistic pairing interaction popping up again. And what we do is we compute the expectation value of the Hamiltonian in a Richardson-Gaudin basis, okay, and find the minimum of that parameter G. And so G does not pop up here in the Hamiltonian anymore. It's a variational parameter. And so here I have variational parameter G. We confronted this with a very small system, 116 just that we could benchmark it. Okay, so the red lines are the benchmark lines where we want to do. And if you then compute this property, you almost, I mean, yeah, this is too beautiful, right? So we did it also for the first excited and the second and the third, etc., etc., etc. So this one, this G minus 0.2 parameter model is a very good starting base to treat this thing, to treat this Hamiltonian that is non-integral. Okay. How good is it? Well, not only we have one state, we have a correlated basis. Okay, so it's like one of those slices in that going up in the symplectic. And what you can do then is, yeah, sort of depicted by this Hamiltonian up here. Okay, so we have a Hamiltonian. It has a dimension of the Hilbert space, and then you can include the first Richardson state, the second one, the third one, etc., 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 diagonalize and see how much it differs from the exact result that you want to go to. Okay, and you can do that for different G's. Okay, so the standard computation you would do is you start from uncorrelated basis states, so just pairing states, G equals 0, and then you start off with a relative one, so it's a relative error. So you started with an error of 1, and then you need almost a whole basis. I think it's 120 here was the full set to reach to a sensible precision on that number. However, if you use that G that was from the variational calculation, the 0.2 approximately, you not only come down a lot more, so you get to, let's say, 1% precision, which is also the reason why it's very difficult to discern visually what the difference is between that blue and that red one over there, and you basically converge exponentially. So at only a few basis states, you immediately get to full convergence. Okay. So I'm no longer working in this field. I moved to quantum chemistry, and again, I said it speaks to David. He pushed me to work on this topic. So because he has an open mind, and probably some of his open-mindedness has also been given to me, because here in Toronto, I started talking with a quantum chemist from Hamilton, in McMaster University in Hamilton. And he learned that I was dealing with these sort of objects. And he said, oh my God, what you've been talking about is what we call Geminals states. I never heard about Geminals states, but they have been on the market since 1953. They were proposed by Leonard Jones, the guy from the potential. So Popol as well is not so well spread, that name in the non-quantum chemistry community, but Leonard Jones it is. And they proposed these sort of states for chemistry. Why? Well, it's a product state, so it's a mean field. So they're supposed to be very tractable, very easy to compute. And moreover, they line up with the physics or the chemistry of molecules. Because what we do, here's my favorite molecule again, it's caffeine. What we do as chemists, we draw, you've done this in high school, you draw these lines between the atoms. And those are electron pairs, Lewis pairs. And here we come again, we have this pair structure, right? However, Leonard Jones himself, he immediately bumped into that permanent problem, right? So he struggled with the combinatorial problem of this. They were computationally intractable and simply abandoned. And well, we were able to rekindle this project, and only like a collaborator of mine had a great paper that was a spotlight in JCP, JChemFis last week. So now I'm a quantum chemist. Here is my group. We're in New Brunswick, Fredericton, which is beautiful nature, beautiful waterfalls. We still work on Geminal theory, but we take a lot of different approaches from different places in physics. We work on symmetry breaking, tensor network methods. We use a little bit of machine learning there. We also do a little bit of quantum computing there. And this is all bagage that I took away from TL. So in conclusion, thanks, David. Question.
How long did you bring to run the airport one day and then figured out
Think about a year. Think about a year, yeah. And it takes some time before you really can get into something, like you really understand something. First is like, oh, I think Trevor also looked into it for a while. At least he told me. I don't really remember. Yeah, we want, I mean, there's integrability there. It's like an extension of so there was this sort of like interest in, this is something that we want to understand. It was only by talking a lot about it that you start to understand that there's also opportunities. I would say a year about, yeah. Because I based my fellowship, which was a year after his year, totally on this project. So it was written in on that, yeah. Oh yeah, no, it takes 10 years. It takes 10 years to develop, to go from something from the idea to really like, there was I read like a book that I read on non-covalent interaction, has nothing to do with this. And there was an introduction, and it says for each scientist has basically have 3 projects in here, because it takes, well, 15 years to bring an idea from idea to like something really like impactful, right? And you'll have like 3 times 15 years, it's like 45 years. So this is the time you have 3 projects in here. This is one of them. See how ambitious I am in the end? I tend to live very long.
Any other questions?